Lecture 21 of Numerical Methods, which is equivalent to Numerical Analysis. In Lecture 20, I talked about divided differences, and I introduced Newton's forward difference formula as part of Newton interpolation. In Lecture 21, we go into more depth about Newton's forward difference formula, and we also talk about his backwards difference formula, still in the context of Newton interpolation. We're doing section 3.3 of our textbook right here, Numerical Analysis. We're actually even not going to quite finish that section even with this lecture, but I'm not going to go any further into the section after this lecture. So what's the plan for this lecture? The first thing to do is review divided differences. These are divisions of differences, that's why they're called divided differences, for certain nodes where we have information about a function, we have data about a function. It actually in general doesn't matter how you order those nodes. They don't have to be from least to greatest. However, when we do Newton's forward difference formula, we do need to go from least to greatest, and we also need to assume that these are equally spaced nodes, spaced apart by delta x, say, although we're going to call delta x h. We'll look at the formula in terms of divided differences and binomial coefficients. S choose k are the binomial coefficients, but in this case, s will not have to be a whole number. We'll look at table/spreadsheet implementation. Our example for this video is going to be f of x equals e to the x. Then we'll look at the forward difference operator, which is not quite the same thing as divided differences, though it's related. And we'll look at the formula for Newton's forward difference formula in terms of this forward difference operator. Third, we're looking at Newton's backwards difference formula. Now we look at equally spaced nodes, but we think of them as going from greatest to least. Least to greatest, we typically write x0, x1 through xn. Going from greatest to least, we'll think of it as xn minus 1 through x0. The formula can be written once again in terms of divided differences and binomial coefficients, though it is with some twists. Then we'll look at the backwards difference operator. Basically, the forward and difference operator are the same kind of thing except with a relabeling. The formula then for Newton's backwards difference formula can be written in terms of this backwards difference operator. This is a real computationally heavy, spreadsheet-focused kind of video. I will also show you some things on my calculator and make drawings on a piece of paper from time to time to help you understand. All right, let's review divided differences in general. We are given any n+1 distinct nodes, not necessarily labeled from least to greatest. Okay, I'm labeling it x0, x1, x2 through xn, and typixally you would imagine those as being in order from least to greatest. But they don't have to be with divided differences in general. We look at their corresponding values, f of xi, for I goes from 0 to n. These are n+1 data points about a function. We're trying to interpolate these points exactly and then approximate the function using the interpolation between the different nodes. The zeroth divided differences are defined to be the function values. So f of square bracket xi is the same of f of xi with curved braces. Those are the same as the function values. We call those zeroth divided differences because they're not really divided differences, but it's still okay to call them that. We can then look at the first divided differences. F of xi, comma xi plus 1, by definition, is this divided difference that you see right there, a division of two differences. You can switch around the order of the nodes in the notation here for these divided differences, because if you switch around the order on the top and on the bottom, you get equality. Essentially, you get two negative signs canceling, and these things are equal to each other. That's a property of divided differences, and it works more generally as well, and that's why it ultimately doesn't matter in this context whether you order things from least to greatest or not. We could talk about second divided differences and third divided differences, and I did that in lecture 20. Let's just jump ahead to the recursive definition of the kth divided differences. Notice here you have k plus 1 nodes in the notation. I'm putting them in a specific order, xi, xi plus 1, xi plus 2, etc. through xi plus k. And it's defined in terms of k minus first divided differences. But amazingly, it turns out you can reorder these things and you're going to get the same thing. This can be done for any I going from 0 to n minus k. Once you've defined these divided differences, you can then define the Newton form of the nth degree interpolating polynomial for these n+1 data points, which is a unique polynomial, though we're writing it in different forms in different situations. Here's the Newton form. P of x equals f of x0, which is f of the first node, using square brackets to be consistent, plus a sum. These are the coefficients. These are the divided differences. They are the coefficients of these products. So think about this. The first term in the sum would be f of square bracket x0 comma x1 times x minus x0 when k is 1, because this is going to be 0 when k is 1. Then when k is 2, this will be an x minus x0 and an x minus x1 will be the last term. You'll have f square bracket x0 through x comma x1 comma x2, etc. If you want, you can think of this product here in terms of product notation analogous to summation notation with a capital pi representing a general product, whereas we use a capital sigma to represent a general sum. But you don't have to. This formula, this assumes that the nodes are in order from least to greatest, x0 through xn, and are equally spaced. In divided differences in general, the nodes don't have to be equally spaced. We're going to let h be delta x, which can be computed as xn minus x0, the length of the entire interval, divided by n, the number of subintervals. For any number x between x0 and xn, choose s. This s is the key thing we want to think about here, and I'm going to make a drawing here showing you what s represents, so that x equals x0 plus s times h. S does not have to be a whole number, though this is easiest to think about when s is a whole number. When s is 0, over here in this formula, when s is 0, you get just x0. When s is 1, you get x0 plus h, which is x1, the next node. We're thinking of them as being in order here. When s is 2, you get x0 plus 2h, which is up to x2, etc. When s is up to n, you get x0 plus n times h. If you replace h with xn minus x0 over n, the n's cancel and it simplifies to xn. But we do want to be able to use this idea even if s is not a whole number. Let me go ahead and draw a picture showing you what's going on here. And in fact, I'm going to focus on the example that we're going to do. In our example, our interval that we're going to focus on is the interval from 0 to 1. 0 will be the 0th node. 1 is going to turn out to be the 6th node, labeled x5. So actually, technically, if this is the 0th node, we'd call this the 5th node, even though it's really the 6th node. And we're going to take delta x, or h equals delta x, to be 0.2. So break this up into 5 subintervals, each of length 0.2. x1 is going to be 0.2, x2 is going to be 0.4, x3 is going to be 0.6, and x4 is going to be 0.8. That's a 0.6 there in case you can't quite see that there. And we're going to focus on trying to approximate the function based on data at these 6 nodes at x equals 0.48. 0.48. How can I write, that's going to be our x. How can I write x? 0.48 as x0 plus sh for some s. I have to solve for s. Well, go ahead and plug in x0 and go ahead and plug in h, which is 0.2, and solve this equation for s. S is going to be 0.48 divided by 0.2, and that is going to be 2.4. Okay, double check that in my mind. Yes, that will be the s that we use for Newton's forward difference formula when we want to approximate the function here at 0.48. And again, the function is going to be e to the x. All right, let's go back to the PowerPoint now. Then we can also do the following. For any number k, that's 0, 1, 2, 3, etc. through n minus 1, we can also write x minus xk in this way. Since x itself is x0 plus sh for some s, and xk is x0 plus kh, when we do the subtraction, the x0s cancel. This cancels with this. And then what's left is sh minus kh. The h can be factored out to leave you s minus k times h. Okay? So we can write that, and that will be helpful for us. So again, our goal is to approximate p of x. Well, x equals x0 plus sh, so we can write this. We want to now write the approximation in terms of s. Here again is the Newton form of the interpolating polynomial f of x0 plus the summation of these divided differences. What are these things here? These are the different x minus x0, then x minus x1, then x minus x2, etc. This is x minus x0 here. Think about what I have here. When k is 0, I'd have s minus 0 times h, s times h. This thing here is x minus x1. When k equals 1 up here, I'd have s minus 1 in parentheses times h, which is what you see. And this right here, if you think about it in relation to this, is going to be s sub k minus 1. When k equals k minus 1, so to speak, I'd be taking s minus in parentheses k minus 1, which simplifies to s minus k plus 1. This is x minus that, I should say. X minus that. Okay, so this is Newton's divided difference formula that I already showed you. Go ahead and simplify a little bit. There are k minus 1 factors of h. There's the 0th factor, the first factor, there are k factors. The first factor is the 0th factor, so to speak. The second factor is the first factor, so to speak, etc. There are k parentheses here, so we get an h to the k when I group all those h's in there together. As far as I have the divided differences going down here. As far as the s's go, I have an s times s minus 1 times s minus 2 times s minus 3, etc. through s minus k plus 1. That's what I have here. Just another way to rewrite it. Now we're going to do something a little strange. It's not necessary to do this. It just could be convenient in certain ways. We are going to multiply and divide by k factorial. Why? Because then this fraction is a binomial coefficient, s choose k, even when s is not a whole number. I can still use the s choose k notation like this. Okay? And so that could be a nice way to program Newton's forward difference formula if you've got binomial coefficients available to you in your program, in your spreadsheet, in Mathematica, in whatever you're using. We have an extra k factorial here. It's not so easy perhaps to program this kind of thing. Okay, this might be a little bit easier. That's the point. And it looks a little bit more compact too. All right, let's look at our example in more depth. So our function is e to the x. Again, we've got 6 nodes, so n is actually 5. We've got x0 is 0, x1 is 0.2, x2 is 0.4, x3 is 0.6, x4 is 0.8, and x5 is 1. So h is delta x is 0.2, like I've already mentioned. We want to approximate f of 0.48, like I've already mentioned. And like I already mentioned on the piece of paper, that means s is 2.4, and you can double check it this way. Here's the table that organizes the work for computing the divided differences. And ultimately, once you've got these divided differences, you can use them to approximate the function. How are these things computed? They're computed with divided differences. Let me, maybe you want to take a picture of that screen here, because I'm about to go away from it and show you some things on my calculator to double check it. Although maybe we can view them both at the same time here. Okay, so here's my calculator. Let's double check some things here with the calculator. So it's a bit small, but let's check this first divided difference right here, this 1.107. That should be, that's f square bracket x0 comma x1. By the way, these numbers are the 0th divided differences. Those are the function values there that you can check at these different nodes. This one is f of square bracket x0 comma x1. That's going to be f of x1 minus f of x0 divided by x1 minus x0. This number minus this number, all divided by this number minus this number. Okay, well, that's pretty easy to do. The top is going to be 1.2214 minus 1, which will be 0.2214. I'll add more decimal places in there. 0.02758 divided by 0.2 minus 0 is divided by 0.2. 1.1070139. That's what this number is, right there, with one more decimal place of accuracy. Let's check this number. That's a second divided difference. It's 0.61273976665 if you can't quite see it. That's, in notationally, that's f square bracket x0, x1, x2. Thinking in terms of the recursive definition of divided differences, that's going to be this number minus this number divided by not this minus this, but this minus this, 0.4 minus 0. Okay, so let's take this number minus this one. This number right there is the 1.352109,697. I'm going to subtract this number, minus 1.1071371. If you can't quite see it, that's what it is. Then divide by 0.4 minus 0, divide by 0.4. Get about 0.6127 or 6124. That's not exactly what you see here, though it's relatively close. I got these numbers in here from a spreadsheet. I just pretty much copied and pasted. So evidently, I think I'm doing a little bit more rounding on the calculator here, and the spreadsheet numbers that you see in the PowerPoint are more accurate. I think that's what's going to happen here. All right, let's go ahead and go back to the PowerPoint itself. Again, maybe you want to take a picture of that. We will look at a spreadsheet here soon to confirm these things as well. Therefore, let's go ahead and use Newton's forward divided difference formula. There's what you get when you plug the numbers in. Where do these numbers come from? The 1.10701338, the 0.61273977, the 0.226103779, the 0.062575, and the 0.01385. Those come from the table. Those were highlighted in red along the main upper left to lower right diagonal of the table that I highlighted in red. Let's just double check that. Again, about 1.1, 0.6, 0.22, 6.06, and 0.0138. Let's see if that's the case. Yes, I'm looking at these numbers on the main diagonal there and seeing these do seem right. That's where those numbers come from. What about the other numbers? Oops, sorry about that. I accidentally pressed hide. Shortcuts are great, but can get in this problem sometimes here. Oops, that's not even the right. That was the wrong spreadsheet. Okay. You see 2.4 lots of places? That's S. There's S. Here's S times S minus 1. Here's S times S minus 1 times S minus 2. Here's S times S minus 1 times S minus 2 times S minus 3. 2.4 minus 3 is negative 0.6. And here's S times S minus 1 times S minus 2 times S minus 3 times S minus 4. So in this computation, I'm not showing the literal binomial coefficients. I'm showing it in terms of the formula before I wrote the binomial coefficients. You also still see h to different powers. H is 0.2. Here we have an h. Here's h squared, h cubed, h to the fourth, and h to the fifth. You might want to pause the video and check these numbers when you simplify, and you get about 1.616079 as our approximation for e to the 0.48. In reality, using a calculator, it's closer to 1.6160744. We're only off in that last decimal spot. The absolute error is about 0.000005, about 5 times 10 to the negative 7. It's a pretty small absolute error. That's very good. Now we want to think of it in terms of the forward difference operator. Got a few more slides for this example, then we'll go to the spreadsheet. Given a sequence, I'm saying real here because that's our application. You could define it this way for complex numbers as well. Sequence Pn for n starting at 0, then 1, then 2, then 3. So this is a list of numbers, P0, P1, P2, P3, etc. We can define the forward difference operator delta, capital delta, that's the symbol for the forward difference operator, to generate a new sequence, P1 minus P0 being the zeroth number in the new sequence, P2 minus P1 being the first, P3 minus P2 being the second. The general equation is this: delta Pn is Pn plus 1 minus Pn for n starting at 0, then becoming 1, then 2, then 3. So yes, this first thing is really the zeroth thing of the sequence, the new sequence. This is the first, this is the second, etc. Okay, and that'll be important to remember notationally as when we compare it to the backwards difference operator. This acts actually kind of like a derivative in a sense for discrete calculus. There's a subject called discrete calculus, maybe you want to look it up. And this forward difference operator has similar properties to derivatives, like there's a product rule, for example. This can be iterated. Just like we can take first derivatives, second derivatives, third derivatives, you can apply the forward difference operator more than once. Get first differences, second differences, third differences. If you apply it twice, you can use this notation here, delta squared Pn. What that really means is delta of Pn. It's not literally multiplying the delta. That's really applying it twice. It's really a function being applied twice. Well, delta Pn is P1 minus P0, P2 minus P1, P3 minus P2. When I apply the delta operator to that, the first term here, analogous to this, becomes Pn plus 2 minus Pn plus 1, up the index by 1 in each case, minus the analog of this, which is Pn plus 1 minus Pn. Simplify that, that simplifies to Pn plus 2 minus 2Pn plus 1 plus Pn. For n starting at 0, then 1, then 2, then 3. It's a new sequence. You can do it again, get a third difference, delta cubed Pn, which really means delta of delta squared Pn, and if you follow your nose through the algebra, it simplifies to this. Once again for n starting at 0, then 1, then 2, then 3, etc. etc. We can write Newton's forward difference formula in terms of the forward difference operator, and that could be perhaps handy. It will be in some ways, we'll see. Note the following. The first divided difference here, this is our symbol for that, which equals this, can be represented in terms of the forward difference operator. x1 minus x0, because our nodes are equally spaced, equals h. And this is the forward difference operator applied to f of x0. It would be f of x1 minus f of x0. Go on to second divided differences. By definition, this is a second divided difference that equals this. And if you simplify that, x2 minus x0 is 2h. And you can simplify the numerators and get this, and you can bring an extra factor of h out to get a 2h squared there. And what's left inside is really delta squared applied to f of x0. Move on to the third divided differences. And in particular, if you follow the logic here, follow the computations, for example, noting that x3 minus x0 is 3h, etc. This can ultimately be written as 1 over 6h cubed times delta cubed of f of x0, where delta again is this forward difference operator. Notice that 6 is 3 factorial, just as 2 is 2 factorial, and 1 is 1 factorial, and our h keeps going up in power as well as the power, so to speak, of the delta operator. In general, you can write this. And the way we're going to use this actually is to multiply both sides of it by k factorial and h to the k. And that's going to allow us to rewrite Newton's forward difference formula like this over here. Because I can replace k factorial times h to the k times this divided difference with delta to the k of f of x0. Okay? It's more compact, that's one nice thing about it. And if you've already got the forward difference operator numbers in a table in a spreadsheet, for example, it could be easier to implement as well. Let's check it for our example. You should take the time to pause and double check these numbers. After you double check it, we're going to go to a spreadsheet. Do notice some patterns here. We have the 2.4 and the 2.4 times 1.4, 2.54 times 1.4 times 0.4, etc. Just like before. 2 is 2 factorial, 6 is 3 factorial, 24 is 4 factorial, 120 is 5 factorial. These numbers are no longer divided differences though. These are values of the forward difference operator. These are these values right here. All right, let's go ahead and go to a spreadsheet now. And let's double check the approximations both with the divided differences on this sheet and also the forward differences on this sheet right here. So let me just clear this out. To first find the more precise value of e to the x, when x is 0.4, I can do equals exp of b2 right there. That'll compute e to the 0.48. To as many decimal places as you see, I'm sure this is as accurate as you can get, 1.616074402. But let's now get our approximation based on a 5th degree Newton interpolation method using divided differences. First, we have the 0th divided differences. These are going to be the function values at the nodes. So I can type equals expb5 here. E to the 0 is 1. Copy and paste these down in the appropriate spots that you see here. E to the first, for example, is e. Now compute the first divided differences. I'm going to go as quick as I can here. Use the 0th ones and do a division of two differences like this. Copy and paste that down. Let's do the second ones now. It's similar. It's once again a division of differences. This time though, in the bottom you're dividing by x2 minus x0. So you get 0.4 minus 0 instead of 0.2 minus 0. These are the second divided differences. Go on to the third ones. Now we're dividing by x3 minus x0. For the fourth ones, has a somewhat similar feel to Neville's method, but definitely is not exactly the same. That was from 2 lectures ago. Okay, so this is a review of divided differences as we did in lecture 20. But now we're going to apply it to approximate e to the 0.48. Thinking about, maybe you want to pause the video and write it down if you didn't, the formula for the interpolating polynomial in terms of these divided difference numbers, these f of square bracket values, where I also multiply by x minus x0 and then x minus x1 and x minus x2 as I keep adding higher and higher powers. F of x0 itself is just this one right there. The first divided difference, fx0 comma x1, is going to be this number. That gets multiplied by x minus x0, b2 minus b5, right? X minus x0. Add on the second divided difference, f of x0, x1, x2, times, I'm just going to type here, x minus x0 times x minus x1. Add on this third divided difference times x minus x0 times x minus x1 times x minus x2 plus the fourth divided difference times x minus x0 times x minus x1 times x minus x2 times x minus x3. Just one more term, plus the fifth divided difference times x minus x0, etc. I'll just try to type as fast as I can here. One more term there. Yes, and you can see the answer is about 1.616. There we go. For a very small error, the error is the actual value minus the approximate value. That goes in alphabetical order. Small negative error here, whose absolute value is, yes, you can see very close to 5 times 10 to the negative 7. Let's do the same approximation with the forward difference formula, and ultimately we'll do it with the backwards difference formula as well. But right now it's just with the forward difference formula. Again, here's our exact value. We want to compute not divided differences, but the values of the forward difference operator. These are the function values here. For the first differences, in the 0 spot, so to speak, would be this minus this, and you don't have to do any division. Copy and paste that down that far right there. For the second differences, do this minus this. You don't have to worry about division. That's the nice part here, is you don't have to worry about dividing. Copy and paste this down. For the third one, I guess I could continue copying and pasting. Copy and paste that to the right. Go down here. Could even do a whole column, so to speak, like this. Copy and paste that here. All right. So these are the values of delta. And across the top, these are the values of delta to the k power of f of x0, along with f of x0 itself. If we're going to use the forward difference formula in terms of these forward difference operator values, though, we need the values of s choose k for different k's. S choose 0 would be just the value of s, 2.4. Let's put that right here. Then we want s choose 1. I guess we don't need the s choose 0. Let me go ahead and get rid of that. S choose 1. That's 2.4. Yeah, it's just the 2.4. S choose 1 would be s. Okay, I'm getting confused. We just have an s term. Hopefully I'm not confusing myself too much. S choose 2, we're going to have s, which is in B, 4 times s minus 1, divided by 2 factorial. 2. S choose 2, what was it, 3 we're at? I'm forgetting. B4 times B4 minus 1 times B4 minus 2 divided by 3 factorial. S choose 4, B4 times B4 minus 1 times B4 minus 2 times B4 minus 3 divided by 4 factorial, 24. Finally, S choose 5, that'll be B4 times B4 minus 1 times B4 minus 2 times B4 minus 3 times B4 minus 4 divided by 5 factorial, 120. So these are the numbers that are going to go in front of these values down here. So the 5th degree Taylor approximation should be, first of all, f of x0, which is this one, plus this times this, etc. I'll just type now. E4 times E7 plus F4 times F7 plus G4 times G7 plus H4 times H7. There we go, 1.616075, approximately the same number as this, okay, with the same error. All right? All right, it's easy to make mistakes there. I got it right. Let's now go on and look at the backwards difference formula right here. Now let's assume the nodes are ordered from greatest to least, still equally spaced. But in my list, I start with xn, then I have xn minus 1, then I have xn minus 2, where xn was the biggest number, down through x0, which was the smallest number. I'm still going to take h to be positive, though. H is still going to be delta x, xn minus x0 over n, still positive. The s, however, will be negative. This time, for any number x between x0 and xn, choose a negative s between negative n and 0, so that x equals xn plus sh, or s, unless x equals xn, will always be negative. Let me go ahead and make a drawing of this one. So now we're going to be thinking about, well, actually let's go to the next line here. For any k from n down to 1, we can write x minus xk like this, because the xn's cancel here, and everything else you can factor out in h, and you're left with this s plus n minus k in parentheses all times h. Let's look at a picture here. use the same picture actually. X is still 0.48, okay? But now we're sort of going backwards a certain number of steps from x5 back to this. By the way, the fact that in the previous one s was 2.4 means that to get from 0 to 0.48, you got to go 2.4 steps, so to speak, where the step size is 0.2. To get from 1 back to 0.48, how many step sizes do you need to do? 1, 2, 2.6 maybe? Should s be negative 2.6? Now we would want x, which is 0.48, to equal xn plus sh, where xn is 1, and again h is 0.2. And we can solve this equation for s. Subtract 1 from both sides, you'll get negative 0.52 equals 0.2s. So 0.2s, or s is equal to negative 0.52 divided by 0.2, and that indeed is negative 2.6. Okay, negative 2.6 times 0.2 would give you negative 0.52. That does work. So s is negative 2.6. That's what we will need here with this backwards difference formula, ultimately. And let's go ahead and write the formula now before we end up using it. P of x is xn, P of xn plus sh. I want to write things in terms of h, just like before. But now, again, these nodes are ordered from greatest to least. Xn is the 0th node, so to speak, then xn minus 1, then xn minus 2. We do need to put f of xn here first. And then in the summation, we do need this kind of divided difference. Then where do these come from? This would be x minus xn, not x minus x0. Think about that. When k is n, replace k with n here, you're going to get n minus n is 0. You're going to get s times h. This one is going to be x minus x sub n minus 1. When k is n minus 1, you replace k with n minus 1, the n's still cancel, and you're left with s plus 1, just like you see here, etc. Okay? You can simplify this. There are, once again, k factors of h. You can write an h to the k here. And you have s times s plus 1 times s plus 2 times s plus 3, etc. through s plus k minus 1. You can write that here. Can this be written in terms of binomial coefficients? It doesn't seem like it at first because you're not subtracting 1 each time, you're adding 1 each time. However, through a little trickery, turns out we can write it in terms of binomial coefficients. First of all, we can once again multiply and divide by k factorial. And this thing again almost looks like a binomial coefficients, except we're adding instead of subtracting 1 each time. However, it does end up equaling this. Negative 1 to the k times the binomial coefficient of negative s with respect to k. Why? Because you can factor a negative sign out of each of those if you like, and there's k of them, so you get a negative 1 to the k. And what's left over, you'd have a negative s and a negative s minus 1 and a negative s minus 2, etc. through negative s minus, in parentheses, k minus 1. So you'd have this negative 1 to the k times this binomial coefficient. Here you do keep subtracting 1 each time. Okay, so through a little trickery, you can bring the binomial coefficient into play. Once again, we're wondering if we can write this thing in terms of a difference operator. And you can, but it's called the backwards difference operator instead of the forwards. It's not a ton different. It's just, in a sense, a labeling difference between the forward and backwards difference operators. Once again, we start with the sequence Pn for n equals 0, 1, 2, 3, etc. So this is a list of numbers, P0, P1, P2, P3, etc. And you still get the same sequence out, but you're going to label it differently. The difference operator itself, oops, this should be backwards. This is a typo here. The backward difference operator is not capital delta. This is the word back. It's upside down capital delta, which does have a name, and it's a beautiful name. It's called nabla. I think that's a Hebrew word. Nabla. that I think stands for harp, if I remember correctly, because it kind of looks like a harp. An upside down delta is called a nabla. You might also see this as what's called a gradient operator if you have multivariable calculus. To generate a new sequence, and it's really the same new sequence as with the forward difference operator, except we label it differently. We label the subscript with n starting at 1 instead of 0. So while capital delta of P0 is P1 minus P0, nabla of P1 is P1 minus P0. Kind of weird, but hang with me here. It's worth writing it this way. This can be iterated just like before. We can have nabla squared and nabla cubed and nabla to the k power, which really means nabla squared means apply nabla twice, nabla cubed means apply it 3 times, etc. And the formula looks very similar to with the forward difference operator. But with nabla squared, you start at n equals 2. With nabla cubed, you start at n equals 3. And in general, etc., you are going to have a similar kind of formula related to divided differences that we'll see here in a minute. Okay? That's what we're about to see here. This first divided difference, fxn comma xn minus 1, which by definition is this, can be written in terms of nabla, like that. Nabla of f of xn, not f of x0. The second divided difference can be written in terms of nabla squared, etc. A third divided difference can be written in terms of nabla cubed. Very similar pattern in the bottom. We're dividing by factorials and h to the corresponding power. In general, we have this. And once again, we can multiply both sides of this by k factorial and h to the k to rewrite that backwards difference formula. In this case, like this. Okay, the negative 1 to the k and the binomial coefficient negative s choose k, they have to stay there. Excuse me. It's this whole thing that gets replaced by nabla to the k power of f of xn. Once again, we can apply it to our example, and this is going to be the last thing that we do. Okay, so hang with me here. And get these numbers and get the same final approximation. Notice now s here is negative 2.6. We're doing negative s choose k, and negative 1 to the k in front. Negative s is going to be positive 2.6. Let's be careful. I almost was feeling unsettled about that. This minus sign here comes from negative 1 to the first power. 2.6 is negative s. Because s is negative 2.6, negative s is positive 2.6. Then we have negative s times negative s minus 1. 2.6 times 1.6 divided by 2 factorial, etc. These signs alternate because these signs alternate, though sometimes we also get negative signs here, here, and here, for example, that you have to be careful about. Take the time to pause this and double check it. We'll end by going back to the spreadsheet and applying the backwards difference formula. So I have the value of s here, negative 2.6. I'm going to put negative s choose k in these spots. And the nabla values, the backwards difference values, starting with xn, are these numbers. Now I am sticking with the table written in the same way, going from least to greatest. I could rearrange it and go from greatest to least. That would be okay to do. But I also can keep it the way it is and use these numbers along the bottom. And that's okay too. These are going to be nabla values. All right, so first we want to do negative s choose 1. That'll be the same as negative s itself. So I type equals negative b15. And then negative s choose 2. That'll be negative b15 times negative b15 minus 1 divided by 2 factorial. Negative s choose 3 will be negative b15 times negative b15 minus 1 times negative b15 minus 2 divided by 3 factorial, 6. Now I want negative s choose 4, negative b15 times negative b15 minus 1 times negative b15 minus 2 times negative b15 minus 3 divided by 4 factorial is 24. Just one more. I want negative s choose 5, negative b15 times negative b15 minus 1 times negative b15 minus 2 times negative b15 minus 3 times negative b15 minus 4 divided by 5 factorial is 120. So these are the values of negative s choose k. I have to multiply these values by negative 1 to the k power and also by the values of the nabla operator to get my 5th degree polynomial approximation. F of xn is this number right here. Then I'm going to have a minus because of negative 1 to the first power. This times this. Then a plus because of negative 1 squared. E15 times E10. Then a minus because of negative 1 to the third. F15 times F9. Plus G15 times G8 minus H15 times H7. There we have it, 1.616074895, same number I got with all these other methods. Okay, I hope the punchline at the end was worth it. Thanks for watching.